The next topic is multicollinearity, and just as with omitted variable bias, we care about this because it could affect our estimates. An OLS assumption is that the model won't suffer from perfect multicollinearity. Multicollinearity means that two or more regressors in a multiple regression model are strongly correlated. And within multicollinearity, we find perfect multicollinearity, which happens when the correlation between two or more regressors is perfect. That is, one regressor can be written as a linear combination of the others. Importantly, I want to emphasize that we cannot have variables which are linearly dependent or perfect collinear in our models. This is known as a rank condition, and in particular, the condition dictates that we need at least n number of observations that is higher than k plus 1. In other words, we have more observations than coefficients. And the greater the degree of linear dependency amongst our explanatory variables, our x's, the less information we can extract from them, and our estimates become less precise. To showcase the concept of perfect multicollinearity, I have three examples. Example one is when we include two variables in which one is constructed from the other in a linear way. It is okay to have x squared because that is not constructed in a linear way. In fact, many times we add h squared to our regressions. The example I want to give you is of two variables that would be perfectly correlated. Let's be redundant and let's think about the price of milk in cents. So within the Brazilian data, I'm just going to create a new variable called p milk wet cents, which takes the price of milk during the wet or rainy season and just divides by 100. And then I'm adding to the model, I'm now creating a new model. I'm going to call it mult.mod.2, and I add that new price. But notice that I kept the previous price. And the way I created this variable, it was linearly constructed from the price of milk during the rainy season. I still use Brazil too. And then I look at the summary, and first thing you guys should notice is that we have NAs for the new price variable. So R knows that they're perfectly collinear, and as a result, because of the perfect multicollinearity, it removes that variable. So R notices the problem and shows NAs for the perfectly correlated variable within the output, so it will never include both price of milk in reais and price of milk in cents. We can look at the COEF test and you see that that new price is not part of the output. Example number 2 is going to include a variable full of ones. Why? Because that's going to be perfectly correlated with our intercept. I'm just going to generate such a variable, so I'm going to assume that all household heads are male. This is a strong assumption. It may not be realistic, but for the purpose of explaining you this possible issue with perfect multicollinearity, I'm creating this variable. So within Brazil 2, I use mutate to generate a variable named male that takes a value of 1 for every household. And I can check that. If I do table, I find that I have 581 ones. And then I add male to model 1. So I'm not longer including the price in cents as in example 1. I remove that. I keep my initial model, and the only thing is I add male. By adding male, now you can see that the output, we have the same situation. Male is flagged and we don't get any output when we use summary. And if we use COEF test, we're not going to see male on the output either. The last example is when we include all possible categorical variables, forgetting to exclude one. So anytime we have a categorical variable, whether it is an education category or a region category, we always need to exclude one of the levels. So suppose we wanted to add the study region to our model. We could create a dummy variable for each region. I can do that. I first figure out, okay, we have 3 levels, center, north, south. I use mutate to create 3 dummy variables, one for north that takes the value of 1 if study region equals north, or 0 otherwise, and so on. And I checked that I created those correctly by doing table Brazil 2 $sign north, and I noticed that I have the same number for north as the ones in my dummy variable. We can do the same for center and for south, and I can check that I created the dummy variables correctly. Then I add the 3 dummy variables to mod1, to our initial model. So this is the only pieces that I changed relative to mod1, and of course the name of the model. And then I look at the output, and you notice that for south, you do not get an output. It gives you NAs. So anytime you have a categorical variable, R is going to exclude one of the levels. And R can do it automatically if we just enter study region. So instead of doing the 3 dummies, I'm simply putting study region in the model as an X. And what you find is that R basically chooses one of the categories to be excluded. So in this case, the level that was excluded was center, and we get information coefficients for north and south. If we do the t-test, the coef test, we don't see center. So this is true for both outputs. Notice that center is not part of the output. So R does it automatically. However, it is possible that you may want to include specific levels. So if we think about geography, it may be best to exclude one that is at one of the edges. If we think about the order of geography, so we may want to include either south or north, but excluding the middle one may not be as intuitive.